All right, last time we were discussing linear systems, and we left off with this idea that if you have a linear system, there's three possibilities. The system has exactly one solution, no solutions, or infinitely many solutions. And we said that it's consistent if it has either one solution or infinitely many solutions. Inconsistent means that it has no solutions. Now, what we want to do is start working towards actually being, coming up with a way to find the solutions. And so that's the direction we're going to take. So remember, here's our general linear system right here. I have it written down already. This is the system that I'll refer to as star. Now, given this system, and this is something that I think you've known this for a long time. So there are three basic operations that preserve the solutions to star. So when you have a linear system, there are certain operations that you can do to this system that will not change the actual solution set that you have. So the first operation, multiply a row by a non-zero constant. So if you take any, did I spell it right? Yeah, multiply. Looks kind of funny. Okay. If you take any row, multiply that row by a non-zero constant, the resulting linear system will have exactly the same solutions. All right, so there's number one. Number two, interchange two rows. Right? If you have a linear system and you take row 3 and you interchange it with row 7, the set of solutions is going to be exactly the same. The third one, add a multiple of one row to another row. All right, so if you take one row, multiply it by some constant, and then take the result and add that to another row, that also will not change the nature of the system. Okay, now, writing down a linear system is kind of a cumbersome process, right? Because you got all these coefficients multiplied by variables, add all that stuff together. What we want to do is simplify the notation. So we simplify the notation of star, and I'm sorry, I want to leave this up, so I'm going to have to erase this stuff right here, but here's the idea. We want to simplify the notation of star by recognizing that we don't need to write down the pluses. We don't need to write down the x sub i's. All that really matters when it comes to this system are the coefficients. And so, here's what we write down, and this contains all the information that we need about our linear system. I just write down the coefficients, a11, a12, da, da, da. It's understood that there is a variable x1 involved. It's understood there's a plus sign. Write down this next row right here corresponds to the second equation, and then we go all the way down to the bottom. This would be a am1, am2, am3, dot, 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 amn, b sub m. This right here is called the augmented matrix corresponding to the linear system. Augmented matrix corresponding to star. Carries all the same information about the linear system. Right? All that we care about are the coefficients, so that's the point. Now, as we mentioned a minute ago, there are three basic operations that you can perform on this linear system that don't change the solutions. that will mean that there are then three corresponding operations that we can perform on the augmented matrix that will not change the nature of the solutions. And so I want to write these down. And these are called elementary row operations. The first one, multiply a row by a non-zero constant. The second one, interchange two rows. And the third one, add a multiple of one row to another row. So these three operations right here correspond to the operations we discussed that you can do to linear systems. They will not affect the solution set of the linear system. Right? And these are called elementary row operations. Now, what we're going to do, right, our goal is to find the solution set to a linear system. And it turns out that starting with the augmented matrix, we can perform elementary row operations, and that will get the matrix into a form where it's easy to extract the solution set. Okay, so I'm going to say that we will apply elementary row operations to our augmented matrix to obtain a form where it is easy to identify the solution set. Right, so that's the idea. And this process, so the process of applying elementary row operations to our augmented matrix to get it in a form where we can say, oh, here's exactly what the solutions are. This has a name, so it's called Gaussian elimination or Gauss-Jordan elimination. Okay, so here's some properties. So let's consider the following properties that an augmented matrix may have. Okay, there's going to be four properties. The first one, so if a row has a non-zero entry, then the first non-zero entry is a 1. And this 1 has a name, right, called a leading 1. Second property. Now, so here we're referring to rows that have non-zero entries. It's possible that you have a row that consists entirely of zeros. such a row needs to occur at the bottom. So rows consisting entirely of zeros are at the bottom. So there's property 2. Property 3. The leading one of a row occurs to the right of the leading ones above. And the last property, if a column has a leading one, right, then all other entries in that column are 0. Right, so there's 4 properties. Property 1, right, if a row has a non-zero entry, then the first one, so as you're reading left to right, the first non-zero entry that you encounter has to be a 1. Second property, all the rows that have just zeros are at the bottom of the matrix. The third one, the leading one of a particular row occurs to the right, right, of the leading ones that occur above it. And then the last one, if, now looking at columns, if you see a leading 1 in a column, all the other entries in that column have to be 0. So if properties 1 through 3 hold, the matrix is in row echelon form. If in addition property 4 holds, so if properties 1 through 4 hold, then the matrix is in reduced row echelon form. I'll abbreviate this one, and we'll see this lots of times, so I'll abbreviate that as capital REF. In the second one, so if properties 1 through 4 hold, it's reduced row echelon form, which I'll abbreviate as RREF. Okay, so let's look at a few examples. And what I'm going to do, I'm going to write all 4 or all 3 examples down, and then we'll take a look at them. So the first one, 1 0 minus 1, 1 0 minus 1, 2 1, 0 1, 0 1 0, and then the last row 0 0 0, 1 2. Okay. So there's matrix number 1. Matrix number 2. 0 1 0 0 0 1 0 0, minus 1 minus 1, 0 0 1, 0 2 0. There's going to be 2 more rows here, so the next one's 0 0 0, 1 1 1, and the last row all zeros. Okay, so there's our second matrix, and then the last of the examples. 1, 0, 0, 1, 0, 0. Uh, 0, 0, 1, 0, 0, 1, and then one more row, 0, 0, 1, 1, 0, 1. Okay, so let's look at each of these three examples and see what we got. So in this first one, let's see, property number 1, as you read left to right, the first thing you want to see, if it has a non-zero entry, the first one should be a 1. So yes, 1, 1, 1. The first non-zero entry in each of these rows is a 1. Second property, all rows with entirely zeros are at the bottom. We don't have to worry about that one. Third property, so what we do now, we look at a leading 1. It needs to occur to the right of all other leading ones above it. Yes? This leading 1 right here also occurs to the right of the ones above it. Last property, if a column has a leading 1, then all the other entries in that column need to be 0. Okay, yes, yes, but no, this one, we've got a leading 1 right here, but they're non-zero entries in the column. So this is in row echelon form, but not reduced row echelon form. Okay, next one. As we go from left to right, the first non-zero entry is a 1. We've got a row of zeros, that's at the bottom. There's a leading 1, it lies to the right of the leading ones above it. There's a leading 1, it lies to the right of the leading 1 above it. And then the last of the properties, leading 1, and if you look at the column, all other zeros, all other zeros, all other zeros. Right, so this one is in reduced row echelon form. Okay, and then this last matrix, so let's see, leading 1, leading 1, leading 1, good. Zeros, there's no 0 rows. Here's a leading 1, it does not occur to the right of that leading 1 right there, so it fails property 3. This one is not in row echelon form. Okay, so that's enough for this lecture. What we will do next is we'll see, first of all, how to get a matrix, starting off with some automated matrix. Using elementary row operations, we're going to get it into row echelon form and then reduced row echelon form. Once we've done that, we'll see that we can, just by looking at it, essentially, we can figure out who the solutions to the linear system are. All right, so we will see you next time.